So what you're looking at here is a cartoon from Vale and Milligan's paper in Science, which is a review paper of exactly this kind of ATP ADP cycling, which is a summary in some senses of decades of work that they have done. This demonstrates the sort of hand over hand movement based on a hybrid of structures, some imagination, some stochasticity, and a lot of artistry. This is not exactly how a motor moves, but this is definitely a conceptual picture that helps us think about it. This is, of course, a single motor, and this is supposed to be kinesin. So the initial stages, it's sort of just landing. There it lands, one head lands, binds to an ATP, exchanging out the ADP. The other one lands, exchanging out the ADP once more, but at the same time, the previous one has digested or hydrolyzed its ATP to ADP, leading to a conformational change and a forward movement. So all this is nice, but when we do this in experiment, this is how we would actually evaluate it. Much less exciting, perhaps, in the sense that what you're looking at in the upper panel is a movie from one of our older papers where we looked at single microtubule filaments that were gliding on a surface that was coated with molecular motors that were pointing upwards. This is otherwise called a gliding assay. And in fact, the context of these is in fact clear in the most obvious cases in spindle assembly, where you're looking in a single one cell stage of the primary division of C. elegans when it divides from 1 to 2 cells, forming in fact a smaller cell in one end. Now, the reason why I bring this up is, of course, these are the so-called cellular and multimolecular applications of these concepts. But in order to make sense of it, in a biophysics course, we really want to go back and look at the models. And one of the most clear models for this has been the so-called thermal ratchet model. And that is the discussion for today. I'm only going to probably discuss the first two figures because of how much time we have left. Um, I hope at least some of you have had a chance to go through the paper. Those of you who have not, after this, please do go through it because I'm posting some questions for you tomorrow. Okay, after the lecture tomorrow. So paper itself is a funny paper. It is an article, but as you might have realized, this article is a review of a lot of different things. Now, according to the basic background, it's obvious that Brownian motion. So this is titled Thermodynamics and Kinetics of Brownian Motor, and it is from 1997. Yes, as the title might suggest, it is effectively putting two things together: Brownian and motor. We talked about motors. We know they're energy dependent. Since 1997, actually, things have progressed quite a lot. Having said that, the theory is in fact still a little murky, and that's partly why we want to go back to the most basic theory and one of the older papers that discussed something called a Brownian motor and its kinetics. So, in fact, as you probably should remember, the idea of a Brownian motor is in a way contrary to the idea of Brownian motion itself. And this is what is illustrated here with the idea that highlighted that a small particle in a liquid is subjected to random collisions with solvent molecules, resulting in erratic motion or Brownian motion, has been described theoretically. And we've spent the whole first quarter of this course discussing Brownian motion, so I really don't want to elaborate on it. Suffice to say that Langevin, who also came up with the same theory at about the same time, divided the forces acting on a molecule into a fluctuating force, both in terms of its direction and magnitude, and a viscous drag force being the two primary motive forces acting on molecules. So if that be the case, then it is reasonable to ask how can we convert this into directed motion, which is what a motor seems to involve, right? And to answer that, we discuss some things about biases in Brownian motion. Now, kind of like your biased coin, your biased dice, something has to change, right? Otherwise, your equal probabilities are clear. You will get non-directional transport. Has any one of you read Feynman's lecture series? Or maybe you had to refer to it in your introductory course, your physics of life, world of physics, sorry. Did any of you do that?
Parts of it, but it's very huge.
Yeah, I know. Did any of you come across the so-called Brownian ratchet or flashing something about ratchets? No?
Yeah, yeah. I've
You remember
read
this
about
picture?
the ratchet. Yes, yes. The
You
ratchet and the
remember this
ball.
picture? Okay, very good. Those of you who don't remember, just let me remind you. This is actually this should read not Paul, but Paul. This is a Paul, Paul, no Pawl, not Paul the boy, but Paul the device, and a toothed wheel, which I hope you recognize by looking at this toothed wheel. That it its teeth, if you look in profile, yeah. If I were to draw this, my drawing is really bad. That's why I take other people's drawings instead. Is not uniform like you would expect a normal toothed wheel to be, a gear wheel, for instance. Instead, the profile of the wheel is such that the teeth are longer in one direction and shorter in the other, tapering off sooner. Yeah. This is what is then called a ratchet. Yeah. Those of you who play badminton, sometimes called the Pune game, you may have recognized this when in the old-fashioned badminton courts when you want to tighten your net. Yeah. Either way, what it does is it allows direction movement in one direction, and this is what the pawl does. The job of the pawl is exactly that, but not in the other. That is to say, you can turn it in this way, but in the opposing direction, there's an enormous penalty due to the presence of this latch or pawl, which itself is spring loaded. So you can keep turning it ahead, but you can't turn it backwards. Got it? Okay, one directional movement. That's one thing. And the second part is that if you want to measure any kind of work being done in an energetic or thermodynamic sense, if you remember last year, we talked quite a bit about this thought experiment of the osmotic engine, and we said that the osmotic engine can only do work if it actually lifts a load, a mass over some height, h or whatever it is, against gravity. Then only can we consider that to be doing work. So in that sense, the thought experiment of Feynman was the following: if you just have a ratchet and pawl, will it spontaneously, using the thermal bumping around of molecules in the air that hit a vane? Yeah, this is a vane, or you can say a windmill or a propeller or whatever you want to call it. uh, Vane is the technical term for this, at least in the Feynman diagram. Diagram by Feynman, I'm sorry. um, in such a case, you could of course get it work done for free, right? I mean, in other words, you have done nothing. There is random movement, and that random movement is converted into directional motion. This is your back to our perpetual motion machines. Yeah. So does anyone want to hazard a guess whether this would work?
Considering the two chambers, then the effect the random motion has on the pedals has the same effect on the pole also. So if it is able to turn the pole, then it can also cancel the effect of the pole also, right?
Very good. Have you read the Feynman ratchet pawl mechanism explanation, or did you think of this right now?
No, like there was another lecture, micro
Maxwell's
motors
treatment,
doesn't do work, like the silicon motors.
silicon motors.
Like they essentially created this
What are
tiny.
silicon? What are you? Can you just? Okay, you read somewhere. Very good, very good. I'm glad to hear that. So, suffice to say, indeed, thank you, Swaraj. So, I'm just going to continue maybe where I was. Suffice to say that only when T1 is not equal to T2, in other words, when there is a temperature gradient, then such a coupling of the Brownian motion with the ratchet pawl mechanism can do work. And this was proof provided by Feynman in theoretical work, and you can go back and refer to it. But given that this basic concept can be made to work in the presence of a thermal gradient, and this is very important, right? That the two things are not isothermal, in other words, then and only then will this work. And this is the reason that Astumian and company in the past have been motivated to look at Brownian motion and its conversion to biased Brownian motion, or what are called Brownian motors. Yeah. So we go to the first figure and look at what they represent here. Um, what you're looking in A at is the presence of two interdigitating electrodes with a spacing of 10 micrometers between them and a small charged particle, this minus sign here, the electron-like object. Yeah, that's your electron. And that this is along some one-dimensional axis x. And the question is, will this geometry give us directional motion? Now, the assumption is that this charged particle is capable of moving randomly, diffusing, in other words, thermally. A similar analogy is also made with, so this was, of course, electrical. So what about biological? So Astumian proposes that a 10 nanometer structure, that is 10 to the power minus 8 meter structure, meaning to say these are something like monomers of 10 nanometers. And this is reasonable for you to assume that it is some kind of protein structure. I mean, 8 nanometers is your dimeric size of a of tubulin, and 4 nanometers is approximately the size of actin, G actin. So this is reasonable number. That they have a charge, a polarity of delta plus and delta minus, which means that they are little dipoles pointing in one direction. And this forming a linear chain allows you, given one additional criterion, that the potential energy, that is U of x here, forms what is now called a sawtoothed potential. Yeah. Does anyone want to try to explain what they understand of this sawtoothed? What is a sawtoothed potential? Perhaps I can leave this slide on. Yes, anybody, anybody. What is a sawtoothed potential?
Sir, it could be a potential having a curve like the sawtooths. Like if we are looking at the peaks, it will be the position where the positive electrodes are, and at one part the negative electrode is close to the positive electrode. Then the gradient will be higher, like the slope will be higher and negative. And in the other part, the electrodes are somewhat more separated, and the gradient will be lower. So essentially having a higher gradient on one side and a lower gradient on the other side.
Very good. Thank you, Swaraj. Exactly. The idea is that and I may have also left out one word that I should have probably mentioned. This is indeed the illustration of an anisotropic sawtoothed potential or a function. You could have an isotropic one. Yeah. So without saying that, it's not really obvious. An isotropic one, just to contrast the two, an isotropic sawtooth would look something like this, where the central point is right at half the width of the tooth. Yeah. Whereas here, it is shifted to one side. As Swaraj correctly points out, that means that the gradient in one direction is sharper than the gradient in the other direction, which also means that since particles follow the minimum potential energy direction, and transitions down a shallower gradient are less like, or transition climbing up a shallower gradient is more likely than climbing up a steeper gradient. You can kind of imagine this might be useful. Okay, so going to the next figure, we'll see what they try to do in terms of implementation, because what you're looking at here is now a further complication of the matter. Earlier, our sawtoothed potential was only in terms of the baseline being flat. Here, in addition, you have a gradient which represents something like a downhill drift. Yeah. So particles like this one here uh, can, of course, at any given time land in the lowest potential well. They can diffusively spread, or they can go downhill down this way, which is where the gradient due to gravity is going to drive them. Yeah, gravity or whatever other gradient that they've set up as a base. And so the energy potential with a so-called fluctuating potential is claimed in this particular figure to be able to result in uphill transport, meaning net transport in this direction. Now, this is a little unusual. Yeah. So, part of the trick, if you want to call it, in this flashing potential or fluctuating potential ratchet is that when the potential is on, there are two states in it, on and off. When the potential is on, the potential energy U on is the sawtooth function minus x of F external. That x times F external is representing the gradient. The periodically spaced wells are at some position IL. Yeah, that is these guys here. I being some index 1, 2, 3, 4. The anisotropy results in two legs of the potential, one at length alpha L, on which the force is delta U upon alpha L plus F external. And so this is now the force, not the energy. That's why you dropped the X. And the other is at length 1 minus alpha L, on which the force is delta U upon 1 minus alpha times L plus F external. So when the potential is off, the energy profile is flat and there's only force of F external everywhere. So if you remember, we went back and forth and we basically concluded in our own course that we would rather stay with the analogy of with the reference to energies, not to forces. But suffice to say that this is not the approach used here. So the Gaussian probability function that results from turning the potential off at t is equal to 0 with particles starting at x is equal to 0. So the particles start here. Okay. Okay. And this is resolved into two components, obviously. One is diffusive, which means they will go in equally in all directions. This way as well as this way. But it is also likely that they will go this way, leftwards, because of the whole intrinsic downhill drift or the gradient. For intermediate times, they argue that it is more likely for a particle to be between alpha L and 1 plus alpha L. Now, this is an interesting argument, yeah? Alpha L is the little bit over here ahead. Now, if you go back and look at the figure, alpha L, yeah, is the peak of the potential gradient. The right-hand side of the drift, I'm sorry, the right-hand side of the initial position. The idea is that this is effectively the distance that in an off state it could travel, and 1 plus alpha L is effectively the next point, the next trough. So why are they even claiming this? Because they claim that it would be trapped in the well at L if the potential were turned back on. The idea is that because of this on and off state, you can freeze the diffusive state temporarily and force things to fall into the nearest potential minimum. So everything that was at this point is all going to fall here. So all of these particles will go here, whereas all these will go back to this minimum point, right? So not much will move from 0. In fact, this will also go here, and this will go here. So from your initial distribution, let us say we started not with x is 0, but a diffusive distribution. Then this part of the distribution, that is the 0 to 1, 0 to alpha, will all shift rightward. The one that was left over here will also shift to the right. And this is what will give you your net rightward current. But in their calculations, and they do an explicit simulation, there's something tricky also about it. And this is the fact that if they take two particle sizes, one which is bigger, which therefore has a smaller diffusion coefficient, and one which is smaller, therefore it has a higher diffusion coefficient. And remember from our analogy about our our entire exercise is about diffusion coefficients and the spread of diffusive spread, that you should get a higher velocity according to this flashing potential on off as the time for which the potential is off is increased from some zero to some non-zero value, reaching a maximum at some approximately 2.5 seconds. On the other hand, the 5 micron particle will indeed undergo negative velocity, and positive and negative is with respect to the x-axis over here. Negative is this direction, positive is this direction. So this should be sort of straightforward. This also means that now if you take a mixture of particles, which is what is represented in C, bigger ones, which are 5 micron assumed to be, and smaller ones which are assumed to be 2 micron, set up a potential which has the same electrode-like nature which we talked about in figure 1, have an overarching gradient. Now you can actually combine flashing potential, that is to say on-off, on-off, on-off potentials, with a gradient to separate large and small particles, with the small particles going up the gradient and large particles going down the gradient. And that's pretty cool. So in a way, with this clever use of a combination of Brownian motion with an external gradient, which they call gravity here, and a flashing potential, which is the bias, you can actually separate particles. And this is kind of a cool application that they claim is possibly implementable. Some of these have been implemented in the past, right? And there are some references in the literature, and there's some interesting arithmetic for understanding this. So for the last two figures in the remaining 15 minutes, the basic mechanism of the flashing potential is illustrated with the shape and the addition of the gradient being described, giving rise to velocities as a function of F max. To conclude, in some senses, they look at the velocity as a function of kBt, which is what our thermal noise is, and they show that 4.1, which is somewhere here, which is our thermal piconewton nanometer, 4.1 piconewton nanometer, which is our ideal thermal regime, is fairly close to a high velocity in terms of the absolute possible maximal velocity, which is seen at 8. In a way, they refer to this optimum that may emerge with increased noise as something that in the literature has been cited as stochastic resonance. And some of you may have come across it in some other unrelated literature in biophysics or physics in general. These are some slightly esoteric phenomena. Suffice to say, the idea is that with increasing noise, in other words, increasing randomness, you can actually get optimal directional motion as they show in this particular case. Okay. In the final figure, they talk about possible implementation by a chemical reaction. And in the first two figures also, they've talked about this chemical product of sulfur and hydrogen breaking up with the addition of an electron, which then they cite as being a possible method by which such a flashing potential might be created, and the fluctuations of charge might be generated due to reversibility. And there's a little bit more chemistry than I want to talk about today. I'm going to end here and simply say that there are umpteen number of experimental data, particularly that they cite in terms of electrical circuits that are implemented, but the exciting part is that the biochemistry of such thermal and directional motion is something that is probably more the domain for chemical biology, biochemistry, and structural biology course. But there are interesting models that come out of it, and we unfortunately, because of a shortage of time in this course, are not going to deal with them. So for the moment, I actually am going to put a halt to this and ask you if there are any obvious questions at this stage. Yes?
Sir, could you explain the point of anisotropy concept? Like how do
Oh,
they measure? I mean, I don't know how do they get the value of alpha out there in the paper?
that's what they put in, right? In fact, as I was trying to, I know I rushed things through, but that was what also Swarag very nicely explained. It's the very concept of the sawtooth potential. In other words, anisotropic sawtooth potential. In other words, if movement in one direction is more gradual or it has a less steep energy gradient, delta U, as compared to the other, then for generating such a so if you on so let us take the counter example. If you did not have an anisotropic sawtooth, you would have an isotropic sawtooth. Okay, and that would look something like this. So the idea is to have an approximately equal length here and here. Saket, are you following?
Yes, sir.
So you can say something like alpha is equal to, um, well, ratios of the halves. Yeah. Actually, maybe how do I put this? So alpha is equal to L. I have to call this something. So L1 by L2. If I now move my sawtooth, if I create an anisotropy, then I'm going to have to do something like this. I'm going to have to move my potential in one direction while keeping the rest of the extent the same. So in my symmetric case, L1 and L2 were identical, whereas in my asymmetric case, LA and LB are not identical anymore. Yes? That's all we were talking about. But what this also means is that the gradient here and the gradient here are not the same. In other words, going down this way is much steeper than going down this way. Or per unit, the distance traveled in y is more here than here. And this means, and anyone who has been on top of a hill knows this, if you're a rock and you're standing on top of this hill, and if the rock can fall either way, if it falls this way, its velocity will be greater, one would assume, simply because it's moving through a larger distance in this direction for the same x displacement. Do you get what I'm saying, Saket?
Yes, sir. Yes.
And this, of course, with the consideration of the flashing potential, means that when there is no gradient, yeah, then they can equally Brownian particles can move equally in all directions, both directions if it's along x. And now you turn back on the potential, yeah. So those that moved here in the next few seconds are going to try and move here, and the rest are going to move here. But because this is a longer region, you're more likely over time to get a frequency distribution something like this. Yeah? In other words, this is fatter than this. It means you will get net rightward movement. And this is how this whole biasing is achieved. Okay?
Yeah. Yes.
In other words, the bias in the gradient gives you the bias in the transport. Yeah. All right.